Here is a combined summary of the two pages. The neutron star interior composition explorer, NICER, has discovered a new accreting millisecond X-ray pulsar. SRGA J144459.2-604207, which underwent a 4-week-long outburst starting on February 15, 2024. The pulsar resides in a 5.22-hour binary, orbiting a low-mass companion donor with a mass greater than 0.1 solar masses. NICER observations during the early days of the outburst revealed a persistent emission spectrum well described by an absorbed thermal blackbody and power law model, with a blackbody temperature of approximately 0.9 keV and a power law photon index of 1.9. A Type I X-ray burst was also detected, exhibiting a plateau lasting around 6 seconds. Time-resolved burst spectroscopy confirmed the thermonuclear nature of the burst, with an additional blackbody component reaching a maximum temperature of nearly 3 keV at the peak of the burst. The discovery of this accreting millisecond X-ray pulsar provides an opportunity to test the limits of accretion physics and refine our understanding of the recycling scenario, where weakly magnetized neutron stars are spun up by accreted material from a donor over Guillot timescales. The Mikhail Pavlinsky ARTXC telescope on the Spectrum Röntgen Gamma Observatory first reported the discovery of this X-ray transient, which was promptly followed up by an array of telescopes and instruments across many wavelengths. The NICER observations were conducted over February 21–23, 2024, with a total good time interval of 9.15 kiloseconds for scientific analysis. The data were reduced and processed using HEA soft version 6.33 and the NICER data analysis software version 12. Accreting millisecond X-ray pulsars are believed to have formed from the sustained spin-up torque provided by accreted material from a donor undergoing Roche lobe overflow over Guillot timescales. By comparing the expected accretion luminosity produced by different orbital angular momentum sinks and the observed accretion luminosity during outbursts, these systems can be used to test mass transfer scenarios. The discovery of additional accreting millisecond X-ray pulsars with all-sky multi-wavelength monitoring of transient outburst activity can further refine our understanding of these extreme systems. Here is the combined summary of pages 3 and 4. The authors present the discovery of an X-ray pulsar, SRGA J144459.2-604207, using NICER observations. They corrected the photon arrival times to the inertial frame of the Solar System using the Solar System Barry Center corrections and the JPL Delaware 421 Solar System ephemeris. The spectral analysis was performed using XSPEC 12.14.0, and the NICER 3 SPECT spectral product pipeline was employed to generate spectral products. The authors searched for coherent X-ray pulsations using the Fourier domain acceleration search (FDAS) method implemented in Presto. They found significant candidates in several GTIs within the 2.0–10.0 keV band, with a trials adjusted significance of 11.3 sigma. The pulsation signal was characterized by deriving a provisional circular orbit model, performing an epoch folding search, and modeling the residual frequency variations. The authors optimized the pulse significance by calculating the statistic with 2 harmonics and found that it was maximized for the energy range 1.03 to 11.97 keV. The authors generated 19 pulse times of arrival, TOAs, with the photon TOA.py tool and correlated them with a pulse template using all the data. The TOAs were then fit to the L1 binary orbit model, yielding the best fit orbital ephemeris. The corresponding pulse arrival time delay is shown in Figure 1c, illustrating the best fit orbit solution. The final folded pulse profile is presented in Figure 1d, showing a significant second harmonic. During the NICER observations, the authors detected a Type I X-ray burst, characterized by a sharp, short-lived increase in the X-ray flux. They fitted the light curve evolution using a hybrid fast-rise exponential decay (FRED) model with a plateau, which significantly improved the residuals around the burst peak. The best fit parameters are given in Table 2, and the results of the fit are shown in Figure 2. Here is a combined summary of pages 5 and 6 of the research paper. The authors present the discovery of SRGA J144459.2-604207, an accreting millisecond X-ray pulsar, and its type I X-ray burst. They report on the initial NICER observations of the source around the peak of the outburst, from 2024 February 21 to 2024 February 23. The timing model for SRGA J144459.2-604207 is presented in Table 1, which includes the right ascension, declination, spin frequency, spin epoch, binary period, projected semi-major axis, and epoch of ascending node passage. The authors perform a phenomenological fit to the light curve of the type I X-ray burst using a simple Fred model and a model with a Fred component and a plateau. The fit with the hybrid Fred and plateau model is significantly better, and the systematic residuals around the plateau are minimized. The best fit parameters from fitting a Fred or a Fred plus plateau model to the Type 1 X-ray burst light curve are presented in Table 2. For spectroscopy, the authors define several intervals for spectral extraction, including the preburst and burst intervals. They adopt a line-of-sight hydrogen column density of NH equals 2.9 times 10 to the 22 square centimeters and employ an absorbed thermal blackbody and power law model. The spectral fits are restricted to 1.010.0 keV as the soft X-rays were absorbed below around 1.0 keV due to the high NH, and the background dominated above 10 keV. The authors present the spectroscopic results for individual OBS IDs in Table 3, which include the blackbody temperature, blackbody normalization, photon index, and power law normalization. The absorbed 1.010.0 keV flux is also reported. Next, the authors analyze the preburst and burst intervals and perform time-resolved spectroscopy starting from 5s before burst onset to 40s after burst onset. They use dynamically binned spectra and generate associated responses using NICERL 3 spect. The spectral fits are restricted to 1.06.5 keV as the background dominated above 6.5 keV. The authors discuss the implications of their findings, including the determination of the binary orbital parameters of the SRGA J144459.2-604207 system, which allows them to constrain the properties of the companion mass donor. They employ the binary mass function to constrain the donor mass radius curve, assuming a Roche lobe-filling donor. The authors also plot mass radius curves for several companion types, including white dwarfs and zero-age main sequence stars. Here is a combined summary of the 2 pages. The discovery of SRGA J144459.2-604207, an accreting millisecond X-ray pulsar, AMXP, is presented, along with its type I X-ray burst characteristics and companion properties. Time-resolved spectroscopy of the burst reveals a cooling blackbody, a signature of the thermonuclear nature of the burst. The period density relation estimates a stellar mean density of around 4.0 grams cm-3, suggesting an early M-type main sequence donor. The mass radius curve intersects with the main sequence companion at around 0.65 m circled dot operator, implying a probability of 11% for binary inclination. Most of the probability space lies above the main sequence in the mass radius plane, indicating stars larger than a main sequence star at the same mass. The companion star is likely very old, tilde operator gear, given the recycled nature of the system, and stellar isochrones suggest a lower, more plausible, mass. The spin and orbital properties of SRGA J144459.2-604207, along with the derived companion properties, fit well within the population of known AMXPs with main sequence companions. The type I X-ray burst light curve profile is best fit with a phenomenological hybrid fast-rise exponential decay and plateau model, with a burst duration of less than 100 s, suggesting low accretion rates of mixed He material. The peak bolometric unabsorbed flux implies an upper limit on the source distance of d less than 10.6 kpc. Subsequent observations have detected more type I X-ray bursts, including quasi-periodic burst trains with a burst recurrence rate that is a function of the outburst flux. Assuming an averaged unabsorbed bolometric flux, The source luminosity is estimated to be L less than 9.5 times 10 to the power of 37 erg-s. If spin equilibrium is assumed, the dipolar NS magnetic field is approximately B less than 6.696.6 times 10 to the power of 8 g, which is within expectations from the distribution of estimated magnetic field strengths of AMXPs. Further X-ray monitoring observations will be crucial in detecting the rising outbursts of SRGA J144459.2-604207 to further constrain the source properties. Here is the combined summary of pages 9 and 10 of the research paper. The authors acknowledge the use of various software and data sources, including Ipython, TQDM, HEA-Soft, and Maxi data provided by Riken, JAXA, and the Maxi team. The research was supported by several institutions, including NASA, the National Institute for Astrophysics, and the Italian Ministry of University and Research. The paper presents an extensive list of references, covering various topics in astrophysics, including neutron stars, X-ray binaries, and timing analysis. The authors cite works on the timing properties of accreting neutron stars, such as the discovery of KHZ quasiperiodic oscillations and the modeling of these phenomena. The references also include studies on the properties of neutron stars, including their masses, radii, and spin periods. The authors cite works on the effects of magnetic fields on neutron star properties and the impact of accretion on their evolution. Several papers on X-ray timing analysis are also referenced, including studies on the application of Fourier transform techniques and the analysis of power spectral densities. The authors cite works on the detection of quasiperiodic oscillations in X-ray binaries and the implications for our understanding of these systems. The list of references also includes papers on the instrumentation and data analysis techniques used in X-ray astronomy, such as the development of the NICER instrument and the analysis of its data. The authors cite works on the calibration and validation of X-ray telescopes and the development of software tools for data analysis. Overall, the paper presents a comprehensive review of the current state of knowledge in the field of X-ray astronomy, with a focus on the timing properties of accreting neutron stars and the analysis techniques used to study them. Here is a combined summary of pages 11 and 12 of the research paper. The authors present a comprehensive study on the SRGA J144459.2-604207 AMXP discovery, a crucial area of research in high-energy astrophysics. The paper draws upon a vast array of previous studies, citing over 40 references to establish a solid foundation for their investigation. The authors utilize a range of computational tools and software packages, including HEA-Soft, Presto, and SciPy, to analyze the data and perform simulations. The paper focuses on the timing and spectral analysis of the AMXP, employing techniques such as Fourier transform and pulse profiling to extract valuable information about the source. The authors also delve into the theoretical aspects of AMXP formation and evolution, citing works by Tout et al. 1996, and Petruno and Watts, 2021. The results of the analysis are presented in the form of figures and tables, showcasing the pulse profiles, power spectral densities, and spectral energy distributions of the AMXP. The authors discuss the implications of their findings, comparing their results to previous studies and highlighting the significance of their discovery. The paper also touches upon the limitations and assumptions of their study, acknowledging the need for further research to fully understand the complexities of AMXP behavior. The authors conclude by emphasizing the importance of continued monitoring and analysis of SRGA J144459.2-604207 to uncover the underlying physics of these enigmatic sources. Overall, the paper presents a meticulous and thorough investigation into the properties and behavior of SRGA J144459.2-604207. Contributing significantly to the field of high-energy astrophysics and paving the way for future research in this area.